my god, it's really, really sour.
It is, right? Because it's been there for a week.
What?
Yeah, it's been there for a week.
Seriously, what happened to the alcohol?
Probably oxidized, right? To give us acid. Remember the reaction we saw in 7.4?
Oh my gosh, I think you're right.
Yeah.
Hi guys, welcome back. Let's do a quick recap of what we have done in the previous lesson. Now, we understood that alcohols, right, can either act as an electrophile or a nucleophile. Now, let's take a look at its role as a nucleophile. Now, a halogen alkane, I'm going to put it at the side, is behaving as an electrophile due to the electron-deficient carbon atom. So, your alcohol at the side is going to act as a nucleophile. It is going to attack the electron-deficient carbon atom, causing the CX bond to break.
Oh wait, Mr. Lang, not so fast.
Oh,
now,
okay.
Alcohols are actually weak nucleophiles, right?
Oh, it's a weak nucleophile.
Yeah, because the lone pair on oxygen, it makes it delta negative. So it's not a full negative charge, it's actually a weak nucleophile. Now, if you look at the Rx there, again, you can see that the carbon is a delta plus. So it's a weak electrophile. Now, Mr. Long, do you think weak nucleophiles can react with weak electrophiles?
I think that is quite unlikely.
Very right. So the first thing that we need to do, remember guys, we have to convert the weak nucleophile, the alcohol, into an alkoxide anion to make it a stronger nucleophile by granting it a real negative manly charge, right? Yes.
So this is going to be a strong nucleophile, and how are we going to achieve that? You say that, I am going to use the reagent, which is going to be a very reactive metal, either sodium or potassium, done at room temperature. Now, the specific thing about this reaction is that you only produce half a mole of hydrogen gas, right? So that's something that you must pay attention to. Even though you start off with 1 mole of alcohol, you end up with only half a mole of your hydrogen gas.
Yep.
Now, the moment you generate a strong nucleophile, you say that I'm able to attack my electron-deficient carbon atom, the weak electrophile, and that is going to be known as the
Williamson ether synthesis. Not Williamson, Williamson ether synthesis.
Thank you for being lame, Mr. Tim.
Emotional, damn it!
Okay, hey guys. So what we have here is I am the halogenal alkane, okay? My butt is the carbon, right? And this bottle that I'm holding is the halogen. So my carbon is electron deficient.
Right, and I'm the nucleophile. I'm the RO minus, and because of the minus charge, it's going to be a strong nucleophile. So we're going to see a backside attack of the RO minus against the halogen alkane. So let's begin. So I'm going to come in to attack the electron-deficient carbon atom, and you realize that the halogen, which is a living group, is going to be expelled. Now, if I look at this, you notice that the halogen alkane has changed its configuration. Originally, it was
like that. I started off like that.
Yes, and after that, now it becomes the other way around. So this is what we call an inversion of stereochemical configuration, right? So this is going to be a quick understanding of how the SN2 mechanism is looking like. Oh my gosh, that was certainly a very visual presentation that is going to be imprinted in my mind for the longest time. So now, if I conclude this Williamson ether synthesis, right, I'm going to step into the shoes of a halogenal alkane. Halogenal alkane is going to be an electrophile, so they are going to undergo nucleophilic reactions. And more importantly, I do notice that the X is going to get replaced with an RO, right? And we're going to create this thing called the ether, right? The ether, the characteristic thing is that the O is going to be bonded to 2 carbons on the left and on the right, right? So therefore, we're going to see this as a substitution reaction. In total, we call this a nucleophilic substitution reaction.
Now, in reaction 7.3, what we're doing here is that we're taking an alcohol and we're converting it into an RX, okay? Now, there are 4 reactions here for you guys to, that you need to know, but I will just be talking about reaction 3 because I like to use that one the most, all right? Now, what we're doing here is this. We have an alcohol, and we're going to use PCl5 solid, and we're going to convert the ROH into an RCl. Now, this reaction is actually quite complex, the mechanism, so we're going to dumb it down a little bit. So how this mechanism works is as such. From the PCl5, we're just going to take out the Cl minus from it. So Cl minus is going to attack the electrophilic carbon in the alcohol, and it's going to break that CO single bond. Okay? Now, doing that helps us generate an RX. So if you guys step in the shoes of the alcohol, notice this. The nucleophile Cl minus is coming in and substituting away my OH alcohol functional group. So this is what we call a nucleophile, substituting away nucleophilic sub. All right? All right. Now, if you guys take a close look at this reaction, there are 2 things that you need to remember. The PCl5 needs to be completely dry. There must be no water present. So this is what we call an anhydrous condition. Because if there's water present, your PCl5 reacts with the water molecule and becomes phosphoric acid. And we don't want that because we want the PCl5 to react from alcohol and not break down. Okay? Now, the next thing that you also must know is this. When the ROH reacts with the PCl5, it releases off HCl as a byproduct. Now, the HCl, because this whole reaction is done with no water present, it will actually escape the flask as a dry white fume, right? As steamy white fumes. Okay? So these are 2 things that you need to remember.
Alright, now moving on to the next reaction that we saw is going to be talking about the oxidation of alcohols. Now the very first thing they must pay attention to is to understand the classification, because different classifications will end up with different products, right? So if you are a primary alcohol, if you perform oxidation all the way through, you say that I'm going to end up with a carboxylic acid. But this is a very special oxidation because it's a stepwise oxidation. It is in fact going to oxidize to an aldehyde first before turning into a carboxylic acid. So if you want to go all the way through, means that you want to get all the way to carboxylic acid, you will use the harsher condition, meaning that you're going to use the stronger oxidizing agent and you're going to do it under reflux. But let's say that if I want to do an aldehyde, if I want to achieve an aldehyde, the conditions must be a little bit more controlled, a little bit more restrained. Mr. Tim, what would that be?
You're going to distill instead.
Distill, and what kind of oxidizing agent are you going to use?
You're going to use K2Cr2O7, for sure, a weaker OA.
That's right, that's a weaker oxidizing agent, right? Now, let's say if you happen to start off with a secondary alcohol, then you are no longer going to get a carboxylic acid. So upon strong oxidation, either using your manganate or your dichromate, we are going to end up with a ketone. Now the last case is going to be the best, because for a tertiary alcohol, you tell me that they can no longer undergo any sort of oxidation. The reason why is because there is no H directly attached to the carbon that allows your KMnO4 to oxidize them. Okay?
Now guys, what we have here is reaction 7.5, and in reaction 7.5, what we're going to do is that we're going to take an alcohol, and we're going to eliminate water. We call this dehydration. Now, how do we do that? We're going to focus on the carbon that's holding your OH functional group. Okay? Now go to an adjacent carbon and circle that H. Now we're going to circle the water molecule entirely, and we're going to remove that water and put a double bond between those two carbons there. Okay? Now Mr. Long, can you tell me what functional group have I just formed?
CC double bond, that's going to be called an alkene.
Yeah, and if you actually take a closer look at this reaction, notice how we just produced water, right? And so therefore, we need a dehydrating agent
That's right.
to kind of pour that water for us, okay? So we use concentrated H2SO4 in excess, or we can use aluminum oxide, okay?
Now, you do realize that for an alcohol, when you do elimination, we always look out for the H that is adjacent to the alcohol. So if I take a look at an asymmetric alkene, where you start to notice that there are going to be two options, you can eliminate either left or right, it should not come as a surprise to you that you're going to result with two different alkenes, right? So if you eliminate left, you're going to get the first alkene, and if you eliminate right, you're going to get the second alkene. Now, Mr. Tim, do you think these two alkenes are formed in equal proportions?
Highly unlikely, right?
Okay.
So if you have two alkenes that can form, then we have to apply Sayzeff's rule. And Sayzeff says this. He says that the more substituted alkene will be the more stable alkene.
Okay.
Now, so do this with me, Mr. Long. Can you box up that carbon double bond? Can you tell me how many R groups do you see that's bonded to that CC double bond?
So I've circled this for you. You realize for the first one there's only one, but for the second one you observe that there are two R groups.
Right. So we call this monosubstituted alkene on the left and a disubstituted alkene on the right.
Okay.
Now Sayzeff says that the more substituted alkene will be more stable and therefore the major product.
Nice.
And there we have it. Yeah.
Cut, take 5.
Oh, wow, Tim, filming with you really very strong. When I film with Mr. William, right, he only just have 1 ng, you know. Yours halfway through already got 30 already. Seriously. Whoa, Mr. Tim, what is that smell?
Is this my new Dolce & Gabbana perfume?
Huh? What was that? It looks so atas. Huh? Dolce and banana? What's that? How much you pay for it?
I paid $150, man, for 100 mils.
Huh? What is inside that $135, $150?
Well, chemistry related is an ester.
Oh,
Yeah.
okay.
Sweet smelling is an ester.
Actually, I got a better way of manufacturing an ester without paying $150.
Oh.
That's going to be 7.6.
Oh, right.
Shall we take a look at this? Okay, shall we take a look at reaction 7.6, which is going to be a more cost-effective way of trying to get a perfume, right? Instead of paying $135 for Dolce and banana. So this reaction itself, we are going to form an ester, which is a sweet-smelling liquid. The characteristic is that you see a C double bond O with an O just adjacent to it. That is called an ester functional group.
Yep.
Now, how do we manufacture it? We definitely need an alcohol, but we are also going to need a second reagent, which has going to be two choices. Mr. Tim, can you remember me what that is?
Well, we can either use the carboxylic acid or we can use an acyl chloride.
Okay, so there are two options over here. Now, what I'm going to do next, right, is I'm going to show you where the atoms are moving. So I'm going to use 3 different color highlighters to help me to illustrate the atom movement. Okay, so the first color is going to be yellow. Now, What's going to happen over here during the reaction itself is that we're going to break the OH bond from the alcohol as well as a CO bond from the carboxylic acid. Now, these two things, I'm going to highlight the H and the OH. They're going to drop off. What are they going to form, Mr. Tim?
Water, H2O, right?
That's right. So you're going to form a water as a side product. Now, whatever that's going to be left behind is going to combine together. So I'm going to take a second color highlighter, highlight the remaining parts of an alcohol. They are going to be part of this ester over here. As well as the fact that your carboxylic acid, whatever that's left behind, you are going to combine them together, right? You're going to form this white bond over here. And that's how we form the ester. Now, let's take a deeper look into the reactions, the mechanism itself. Now, this is a simplified mechanism. It's not the actual mechanism. So, it's just to help you to understand what's going on. So, Mr. Tim, let me step into the shoes of an alcohol over here. Can you share with me, do you think this is going to be acting as a nucleophile or electrophile?
Well, the lone pair on the oxygen makes the alcohol, again, nucleophilic, right? And if you take a closer look at the carboxylic acid,
Right.
now the carbon there, notice how it's bonded to two very electronegative oxygen atoms,
That's right.
and this makes the carbon electrophilic.
That's right.
Right.
So you realize that there is a nucleophile and an electrophile. So obviously an attack is going to happen. So your O is going to attack the electron-deficient carbon atom, causing the CO bond to break. And that is how we get the ester.
Right.
Okay. Okay, Mr. Tim, let's zoom in into the products, okay? Now, I want to take a look at the water over here.
Okay.
There's a lone pair. What does this make water?
Well, mix water a nucleophile.
Oh, okay, this is a
Yeah.
nucleophile. Now, shall we take a look at the ester as well? I'm going to zoom into this carbon that's part of an ester. What is this ester going to be?
Well, again, the carbon bonded to two very electronegative oxygen atoms. So again, makes the carbon electrophilic. Oh no.
So it's going to be an electrophile.
Yes.
So there's a nucleophile and an electrophile. So therefore, I think that it won't come as a surprise to you that you're going to perform a attack, right? Now, when this happens, what you're going to get as a product is going to be these two original reactants itself. Now, this is exactly the reason why this reaction is a reversible reaction. And that's also exactly the reason why this reaction gives you very poor yield. So if you use a carboxylic acid, the ester that you get is going to be present in very small amounts at the end of the day, even though you leave it there for very long periods of time.
Right.
So Mr. Tim, can you suggest a better method for me?
Right. Yes. So a better method is where we can switch up the electrophile and we use a stronger electrophile called an acyl chloride.
Okay.
Now, at this point of time, yes, you guys have never seen an acyl chloride before. So an acyl chloride functional group is this. Go to the CO, right, box it up. Notice how there's a Cl bonded to the carbon directly to it. This is what we call an acyl chloride functional group. And yes, just accept it. It's a stronger electrophile than a carboxylic acid. Okay. So once again, the alcohol is going to be your nucleophile because the lone pair on the oxygen makes the oxygen electron-rich. So the alcohol nucleophile is going to attack the carbon in the acyl chloride, breaks off that Cl bond, and once again, we form our ester. Okay. Now, because the acyl chloride is the strongest electrophile, you will realize that the backward reaction will not take place anymore. Okay, it will really be pushed forward to the right. Okay.
So can you summarize for me what is happening between using a carboxylic acid as well as an acyl chloride?
Of course. So let's just remind the students again, right? So write this down, guys. Carboxylic acid, weaker electrophile. Acyl chloride, much stronger electrophile. And because of that, you will realize that the carboxylic acid, reversible reaction to form an ester, and acyl chloride, irreversible. So we see incomplete versus complete. Now, once again, because the carboxylic acid reaction is irreversible, Mr. Long, would you expect the yield to be high or low?
I don't think so.
Low, right?
Yes.
So hence we have a lower yield, and acyl chloride will be a high yield.
Yep.
Again, once again, make sense of this. Weak electrophile versus strong electrophile. You're definitely going to need heating for the carboxylic acid, and you can do the acyl chloride reaction at room temperature. And last but not least, again, to make sure that my carboxylic acid's POE is really pushed towards the right, because again, it's reversible, we need to use a H2SO4 dehydrating agent, right? But for the acyl chloride, we don't need it because it's, again, irreversible.
That's right.
All right?
So H2SO4 actually acts as two roles over here. Not only is it a dehydrating agent to remove the water, but we also notice that H2SO4 supplies H+.
Right.
And this H+ is going to be acting as a catalyst for the reaction to speed up the reaction. Because at the end of the day, a reversible reaction is really bad. We want to make sure to get as much yield as possible.
Yeah.
Okay, the last reaction for alcohol is reaction 7.7, or what we call the Iodoform reaction. Okay, now this uses a very interesting reagent condition. We're going to use alkaline iodine and we are going to warm. Now beware, it's warm, not heat. Okay, there's a difference between that. Now what's going to happen over here is that if I take a look at the alcohol is very specific. Okay, not every alcohol can undergo Iodoform reaction. It has to be called what we call a methyl alcohol. So follow me closely. Look at the alcohol. This carbon must be specifically attached to a H as well as a CH3. Now the reason why is because this CH3 during the reaction itself is going to break off, and this CH3 is going to form this CHI3. Right? The I is going to come from the reagent itself. Okay. What is the observation for this CHI3, Mr. Tim?
It's a yellow PPT.
It's a yellow precipitate. And what do you call this yellow precipitate? This is called an iodoform, right? Yeah. So in this case, the CH3 drops off. But what is going to happen to the remaining parts of my organic compound? You see that this part looks roughly like a primary alcohol. So what's going to happen is that your iodine is going to act as an oxidizing agent. So it is going to oxidize all the way to carboxylic acid. Now I hope that this part sounds roughly familiar because from reaction 7.4 we saw exactly the same idea, that you are going to oxidize a primary alcohol to a carboxylic acid. But of course the reagents are going to be slightly different. Okay? But something a bit weird is happening over here. We are using this under alkaline conditions. Mr. Tim, can you share with me what do you think is going to happen after producing this carboxylic acid?
Well, because of alkaline conditions, an acid-base reaction is going to occur, right? So RCOH will become RCO minus.
That's right. And that is going to be one of the main products of my iodoform, right? You're going to produce not a carboxylic acid, but a carboxylate salt. All right? Now, Mr. Tim, can you run us through the key features of iodoform?
Now, yes, so the two features of this reaction is this. Now, the first one, Mr. Long has said, I'll mention again, you need this methyl alcohol structure. So CHOH, CH3, you need those four things there, okay? Now, the next thing is also this. Now, Mr. Long, can you count with me, right? In the product, in a carboxylate salt, how many carbons do you see?
I see one here and one over here, that's two. But in the product, I only see one.
Right. So I'm going from a 2-carbon reactant to a 1-carbon product. This is going to be a step down reaction. Okay?
That's right.
So these are the two things that you must remember.
Now, the last thing that we want to talk about is the fact that just now we said that we cannot have any strong heating. We must do this with warming over here.
Exactly.
So warming is something, I mean, we can also call it gentle heating. The idea over here is because CHI3 is actually a very unstable molecule. Why is that so, Mr. Tim?
So if you draw that structure, Mr. Long, you will realize that iodine is in period 5, right? So we have, it's a very, very fat electron cloud. Now we have 3 of those fat electron clouds on the same carbon.
Right.
It's going to experience so much steric hindrance. Do you think it's stable?
That's why it's not stable.
Yes, it's not. So that's why we cannot heat it. We need to warm. Because if we heat it, it breaks down.
Okay.
Okay. All right. So Mr. Long, what I have here is 1 Ribena, 1 red wine. I'm not sure which is which because I mix them up. Are you able to distinguish them apart?
Of course, come.
No. You can't taste it. You can't taste it.
What? Wait, what? Oh.
Yeah, we need to do a chemical test to distinguish them. How do we do that?
Okay, sure. I'll give you 3 ways to do it, okay?
Okay.
So let's start off with the first one. Now, the first one over here is going to be using a sodium metal, right? Now, let's recall again from one of the earlier reactions. The alcohol can react with sodium, and more importantly, they're going to produce a H2 gas, right? This is going to be observed as an effervescence, and the moment you see some bubbling, I think that is going to be a good indicator that an alcohol is present inside. So that's the first one.
That's the first one. Okay.
How about the second one, Mr. Tim?
Now, the second one that we can use is this reaction 7.5. Remember, now we can take an alcohol and we convert it to an RH using anhydrous PCl5 solid. Remember? Now, if you look at the byproducts, notice how there's HCl produced.
Okay.
Because in the reaction there is no water present, remember anhydrous PCl5, when the HCl is produced, it escapes as a gas. It doesn't dissolve, it escapes as a gas. So if I see steamy white fumes, that's how I know that, okay, there's an alcohol present, right?
That's right. Now, the last one over here is actually the one that is used most commonly. We understood that alcohols can undergo oxidation, but not alcohols can undergo oxidation, right? Which one can't undergo oxidation, Mr. Tim?
So only tertiaries can't.
Yes, that's right. So except the tertiary ones, the rest of them all can undergo oxidation with a strong oxidizing agent. So we can either use potassium manganate or potassium dichromate, and because these two things will have a distinct color change, that can also help us to tell that the solution actually contains an alcohol, right? So just to remind you again, KMNO4, what's the color change, Mr. Tim?
Purple to colorless.
That's right. How about your dichromate?
And your dichromate turns from orange to green.
That's right. So these are the color changes that you must be aware of. Okay. Now, Mr. Tim, let me throw you a slightly harder question. Okay.
Okay.
So let's take back the glass of your wine and your grape juice Ribena.
Sure.
Can you tell me, right, between these three different methods of distinguish between them, which ones are the ones that you're going to choose?
Well, if I try to use the PCl5 one, right, so looking out for that steamy white fumes, but you will realize that, wait a minute, there is water in here, right? So which means the HCl won't come out as a gas, it will actually dissolve inside.
Oh, that's quite
right?
smart, yes.
Now, next one, if I try to use an oxidizing agent, KMNO4,
Okay.
so imagine I put a few drops in, I won't be able to see a color change because it's so red, right?
Oh, right.
So I won't be able to see that purple to colorless or orange to green, right, if I use dichromate.
That's right.
So those two reactions suck. The only one I can really use is taking a sodium metal. So sodium metal, and I put it in, right? Now you would see actually bubbles of H2 gas coming out from the surface. You'll see effervescence, and that's the best test here.
Yes,
Okay.
I do agree, because I mean this is all done under room temperature, right? If you were to do it for KMNO4, you need some sort of heating, which definitely is not such a simple chemical test that we're looking out for.
Yep.
All right, so I think that's all we have so far. So we'll see you in class.